Welcome to this first mini lecture on proving for computer scientists. In this lecture, we're going to talk about what a proof is and why we care about proving. So let's get right into it, and let's start by looking at the definition of a mathematical proof. My definition is the following. It is a convincing argument for the reader to establish the correctness of a mathematical statement without any doubt. And even though it's cliché, let us just look at the different parts that make up this statement. Firstly, it's an argument for the reader, so not for ourselves when we're writing the proof. Because if all is well, when we're writing it, we are already convinced that it's true. So when writing it, we should always take into account that someone else needs to understand what is happening. Secondly, it's about a mathematical statement. So something that is either true or false. And as such, we can also prove that it's true or false. And finally, and I think this is the most important one, it is without any doubt. We are not trying to convince the reader that this may be true or that it intuitively makes sense. No, we are trying to prove that it must be true. And hence, our proof also needs to be some structured, step-by-step mathematical proof. Okay, let's keep these three parts in our mind and let's just store them so that we can think about them while we're looking at the other parts of this mini lecture. And the first thing I want to look at is a claim and see what kind of proofs you could make for this claim. And if I have a claim, then of course I have a problem. So here's my problem. I have 7 socially awkward scientists who want to sit at a table with 14 chairs. Now, given that they're socially awkward and they've had a long day of sciencing, they really prefer not to talk to each other. And being scientists, they thought about this and they figured out that it's actually socially acceptable not to talk to your neighbor at the table if there are at least 2 empty chairs between you and your neighbor. So for the yellow scientist, his neighbor on the right is far enough away as there are 2 empty chairs between them. But on his left, given that there's only 1 empty chair in between, he will have to talk to his left neighbor. Now, being tired and being socially awkward, a scientist is unhappy if he or she needs to talk to both neighbors. Of course, there's 14 chairs to choose from and only 7 scientists, so they can pick which chair they want to sit at, which means there's many ways in which these 7 scientists can sit down at the table. But my claim is, in every possible way they sit down at the table, there will always be at least 1 scientist who is unhappy. Now I challenge you to just pause the video here for a bit and see if you can prove this claim. And keep in mind the 3 requirements for a mathematical proof. And then I'll see you in a bit. Okay, welcome back. Hopefully you actually spent the time and paused the video and you tried to prove that in every sitting there is at least 1 scientist who is unhappy. What I would like to do is just look at some of the proofs that I've seen in order to prove this claim, and I want to talk about why they are or are not mathematical proofs. And the first one is really obvious. I mean, this is the quote-unquote proof. And clearly this is not a proof because it's not step by step, it's not for the reader. If anything, it's just a statement, but it's not a mathematical proof for sure. But what about this proof? It's for sure already a bit more, so let me just give you the gist of it. You can read it in the meantime if you want. The idea of this proof is that it never helps to have a single empty chair between two scientists. So we might as well group the scientists into pairs of two. And then between every pair of pairs, there need to be at least two empty chairs. Now we can do this and we can make 3 pairs of scientists, but then we're still left with a single last scientist. And if we carefully count how many chairs we have, then we cannot make this last scientist happy, because there is not enough chairs left anymore. But even though this intuition and this idea is definitely true, and this is also how one could reason about this and prove this, it is still not a formally closed proof without any doubt. Because there are many places within this proof where I could still wonder why it is the case that this choice was made. And don't get me wrong, I mean, all of these, it's clear that they're good choices and that they make sense. But that's not our goal. We're not trying to prove that it may be true, we're trying to prove that it must be true. Now, maybe at this point you're wondering, who cares? Because it's really obvious that this is true. And it's clear that this is the best way to do it, so why bother? Well, keep in mind that for many of the proofs that you'll encounter as a learner, they will be simple and it will be clear to see that intuitively this is indeed right. But it's also not the goal for you to figure out if it's right or wrong, it's to prove it. Anyhow, just to show you that when you get to harder things, this need not necessarily be true and it doesn't necessarily need to be unique, let us look at a problem which may be counterintuitive if you've never seen it before. It's the Monty Hall problem, and it's the following. You are on a game show and there's 3 doors in front of you, and the host is going to show you these doors. So the host walks by all doors, opens them, and shows that behind 2 of the doors there is a goat, and behind 1 of the doors there is this awesome car that you've always wanted. Of course, you're going to win one of them, but they won't just let you pick. So what's going to happen is that we're going to close all the doors so that we don't know where okay, let's not worry about the logistics. There's 3 doors, and behind 1 of them there is a car. Of course, we don't know which door, so let's just shuffle these doors so that we don't know anymore. Now we have 3 doors, A, B, and C. Behind 1 of them is a car, but we don't know which one. Now the host will ask us, and we get to pick 1 of the doors, and we get whatever is behind that door. So let us assume that we pick door A. Then what the host will do is he will open 1 of the 2 remaining doors, B or C, and show that there is a goat behind it. And now comes the interesting part. At this point, the host will offer us a choice. Either we stay with the door we chose in the first place, door A, or we can still choose to change to door B. But that's the final choice. Then we don't have an option anymore. So either we get what's behind A if we stick with it, or we get what's behind B if we now change our mind. And the question is, should you change your mind? Should you still switch to door B? Or is it better to stay with door A? Or does it really not matter at all? And the answer, may be counterintuitive if you don't know it, is that you really should switch doors. Because the chance is way better when you pick door B that you'll get the car. And you can prove it. But we're not going to do in this video. Okay, this is all for our introductory lecture. There's some more exercises linked, and then afterwards, hopefully I'll see you at the next lecture, which is about logic.